So, hello everyone. Really nice to be here with you today, and let's talk about recent trends in wastewater treatment segment. When we talk about wastewater today, it is no longer a purely technical issue. It is shaped by a mix of regulatory, environmental, and economical forces, all pushing us to do more with less. The strongest driver is regulation. And I will focus here on the European experience because later we will need to integrate it into the Ukrainian law. So new European legislation demands stricter discharge limits, energy monitoring, and even micropollutants removal from wastewater. Then, of course, there is water scarcity. 40% of the European territory already faces seasonal or chronic water stress. Footprint also is another challenge. We have less and less space available to build large conventional plants. Energy matters too, as energy cost is constantly rising. And the focus is shifting from simple treatment to resources recovery, like water, nutrients, energy, minerals, etc. And at the same time, digitalization is becoming part of compliance too. Real-time sensors, smart control, predictive maintenance, and finally, etc. And finally, economic pressure, because technically you can meet all these requirements, but the plant still has to stay profitable. That's why today the trend is towards low impact, fit for purpose solutions that optimize cost and performance. So now let's look first into what is behind this regulatory pressure. The European Urban Wastewater Directive that regulates municipal wastewater discharge this year has been updated for the first time in 30 years. This new 2025 document keeps the same core parameters on organics and suspended solids, but it is introducing lower, stricter limits for nutrients, for phosphorus and nitrogen. And it is also adding first-time regulation on micropollutants. Large plants over 150,000 people equivalent will need to add additional treatment stage, achieving 80% removal of selected pharma and cosmetics ingredients from urban wastewater. And importantly, this stage will be financed by those pharma and cosmetics companies through additional taxes under the polluter pay principle. This directive also adds mandatory monitoring of microplastics, energy use, and greenhouse gases in urban wastewater. And on the right side, you can see the compliance picture. Northern Europe already in blue colors, so it's nearly 100% compliant with old legislation. At the same time, Southern and Eastern European regions still lag, and non-compliance is expensive. For example, Spain pays around 12 million euros every 6 months in penalties until they will completely modernize their wastewater treatment segment. So the pressure to upgrade municipal plants is very real. And this pressure applies also to the industrial sector under the European Industrial Emissions Directive. This is a very complex document that covers nearly all industrial segments: chemicals, metals, food, energy, etc. Each segment has its own document defining pollutants limits and performance levels. This directive was also amended last year, and the new 2024 document goes even further. It adds more industrial segments and for the first time includes water use efficiency as performance criteria. So industrial plants must show continuous improvement, not only in the discharge quality, but in total water use. And emissions data is publicly available through the European Industrial Emissions Portal, meaning transparency and reputational risks are now part of compliance. On this map, you can easily find each and every industrial plant in Europe and see how much wastewater, hazard, non-hazard, etc. they are discharging. And here, unlike in the municipal sector, the industrial company will pay penalties itself, not the government. And these penalties can be severe, very expensive, and they can even lead to the plant shutdowns and criminal liability of the plant personnel up to imprisonment. So for example, 3M Belgium, that you can see here on the graph, recently faced a temporary plant shutdown because of PFAS pollution and paid more than €500 million penalty. Now let's see how this regulatory pressure translates into technology. So in urban wastewater, we see the classic treatment sequence. For the smallest plants, it is primary treatment for solids removal and secondary treatment for organics matter. Larger plants need to have tertiary treatment for nutrients removal, nitrogen and phosphorus. And finally, the largest plants will need to add new quaternary stage for micropollutants removal within next 10 years. Today, the major focus is still on secondary and tertiary stages upgrades to increase the capacity of existing plants and ensure the compliance with regulation for organics, nitrogen, phosphorus, so still even with low regulation, especially big trend in Southern and Eastern Europe, which is still not compliant. And rarely now you can see plants who will do this upgrade through the conventional activated sludge. They use more and more new generation of biological systems. And here I want to talk about 4 of them, which are the most popular today. MBBR, a very quick retrofit option when you're adding special plastic carriers to intensify biofilm growth. It has low capital cost, but high operational cost because of high energy consumption. And it also has a risk of microplastics generation because of attrition of these plastic particles. MBR, very interesting technology, combines biology with membrane filtration. It delivers excellent effluent quality, but has also high energy consumption, and membranes need to be replaced every 5 to 7 years. More novel technologies, MABR. In a simple words, this is advanced aeration system. It's consuming up to 70% less energy than traditional technologies. It's very compact. You can upgrade your plant very quickly, and it's very good, especially for decentralized plants. And finally, granular sludge, also very compact, very energy efficient solution. The only one drawback, it's a bit sensitive to different process shocks because they can damage the granulation process. But now all 4 of them are well recognized globally, and more projects every year happening with these technologies. Each of these 4 options represent a balance between energy, cost, and footprint. And at the end, it's up to the decision of the plant which technology to use, depending on their needs. Now, on another side, let's talk about waste sludge. Each and every stage of biological treatment generates it. First, it should be dewatered and dried. In the past, and still today, it frequently used as fertilizer at the end because it's rich in nutrients, nitrogen and phosphorus. More and more countries, because waste sludge has also a lot of toxic materials, heavy metals, PFAS, and microplastics. That's why some countries now demand incineration of the sludge. And this is costly and energy-intensive process. That's why it is beneficial to integrate so-called anaerobic digestion stage prior to incineration. You will treat your waste sludge in special anaerobic meta tanks to produce biogas. And this biogas then can be purified through conventional or membrane methods to a high purity biomethane. And this biomethane can be used internally in the plant, and many plants already became energy self-sufficient with this approach, or some extra volume, spare volume can be even sold back to the electricity grid, generating additional income for the company. Many great installations already you can find in Europe, but also in Ukraine. And finally, phosphorus. Europe imports 80% of its phosphorus. At the same time, urban wastewater is full of it. You can recover phosphorus from the sludge water after sludge dewatering and drying, mostly in the form of struvite. It's easy to deploy process, but it has quite low recovery rates, 20 to 40%. Or you can recover phosphorus from sludge ashes after incineration with more complex and more expensive technologies like acid extraction or thermochemical treatment, but at the same time, you have very high recovery rate of phosphorus. Some countries like Germany, Austria, Switzerland, already demanding partial phosphorus recovery from the urban wastewater, and it is expected to come to other regions too. So today, modern wastewater plant is no longer just a water treatment plant. It is an energy and resources factory. And now let's talk about water reuse. Traditionally, wastewater treatment plants need to clean their water to the enough good quality for the safe discharge. But because of the water scarcity and increasing treatment requirements, this water will be simply too good for discharge. At the same time, reuse cannot be achieved by adding one simple single technology on top of it. It should have a fit-for-purpose strategy. So let's talk about a few options here. The simplest, the cheapest way, and already the most popular one today, is to treat urban wastewater after biological treatment with sand filtration, ultrafiltration, or MBR modules, and plus disinfection, and you can safely reuse this water for irrigation in agriculture. It's already a mainstream in Southern Europe. So all the oranges, lemons, etc., that are coming from Spain, they're all irrigated with wastewater, purified wastewater. Industrial reuse is another, I would say, the fastest growing application. Both urban and industrial wastewater can be treated with the different combinations of MBR, ultrafiltration, reverse osmosis, ion exchange resins, or EDI modules to achieve the quality needed for any possible industrial process. So you can start with the cheapest option, the simplest one to clean water for the cooling towers feed. This is actually the largest application in industrial segment. Or you can treat the water to the high purity quality required to feed high pressure boilers. Advanced users in industrial segment can also go up to minimum or zero liquid discharge. They use additionally special high-pressure so-called brine reverse osmosis, evaporators, and crystallizers, and they can achieve up to 100% recovery of the wastewater. And finally, potable reuse. Urban wastewater can be treated successfully up to the drinking water quality. And then, in case of direct potable reuse, it will be sent directly to the population. Or in case of indirect potable reuse, you will have this natural buffer in between of the process. I know it sounds not very tasty, but it is already proven to be safe and applied in different regions around the globe, in California, in Singapore, and even in Europe, in France, and in Belgium. Belgium recently started its first direct potable reuse project. At the same time, looking at all these complex schemes, the question is, can we afford it financially? And the answer is yes. Reuse today is economically competitive. I'm sharing here the information about capital expenditures and operational expenditures. So irrigation or basic industrial reuse has already similar cost to natural freshwater treatment. So we will better protect this natural water for the drinking water purposes, even if there is still no water scarcity. The cost of even the most complex reuse schemes is already below seawater desalination. Actually, desal is economically beneficial only for the largest, so-called mega desal plants that they are building in Middle East, etc. Those plants are treating 500,000, 1 million cubic meters per day. We simply don't need them everywhere. So if the need in water is lower than that, and there is a water scarcity, it will be always economically beneficial and environmentally more friendly to go to some of the reuse schemes. Only ZLD, zero liquid discharge, is still more expensive because of very high energy demand needed for evaporators and crystallizers. But ZLD is never used because of water scarcity. ZLD used only if it's demanded by legislation in cases of severe environmental pollution from the previous bad industrial practices. Most of these projects are happening in India and in China. So today, looking at this picture, economics is no longer the barrier. It's actually the enabler of the wastewater reuse. And the question is no longer, can we reuse wastewater? It should be, why wouldn't we? And all these trends lead to one important conclusion. Wastewater reuse is no longer optional. We are facing chronic water stress. New regulation also expects reuse to happen. It is also financially viable, often cheaper than desalination. And finally, we must change how we see the water. It is not a liability or waste, but a valuable raw material. With this, that's all from my side, and let me know if you have any questions, both in English or in Ukrainian. Thank you.